My name is Klaus Iglberger. I work as a freelancing software trainer, software consultant, C++ consultant. But what I really do is I love to talk about software design. Probably because very few other people talk about this, but I really like to talk about breaking dependencies, managing dependencies. And so naturally, I also love to talk about design patterns, these tools that help you to actually manage dependencies. And so today, I want to give you an introduction to the visitor design pattern, which is a pretty interesting design pattern because it is very much different from all the other design patterns. And I'll probably show you why. But I'll tell you a story. So we'll slowly move there by seeing a first example of code. And as in so many other talks, I use a very simple example. I will again just draw shapes, which is good because you do not really have to think about the problem. You can focus on the structure. You can focus on dependencies. And so I start by, say, defining an enumeration called a shape type. And right now I have two of them. I have circles and I have squares. This shape type is used in a class called shape. This is a base class. So in the middle, you see it has a virtual destructor, but interestingly, it has a data member too, a data member of type shape type. So one of these enumerators. There's a constructor that takes a shape type called t, and I have a getType function that allows me to access that type. So basically, I can ask, what are you? Are you circle or are you square or something else? The circle class derives from that shape class. It's a pretty straightforward circle. So the circle, for instance, takes a double value. This is the radius. Initialize its data member. It can definitely take more, a center point, other circle properties, whatever you need. There is definitely some getters. There is data members. But most importantly is list line. I initialize my base class. I'm a circle. I should remember that I'm a circle, so I use the circle enumerator to initialize the base class. Additionally, there is a couple of free functions. There is a translate function, a rotate function, a draw function that allow me to draw a circle by some offset, some angle probably, and perhaps there's some more stuff for draw. Okay, the circle doesn't want to be alone, so there is a square too. The square class, however, is super similar. So we do not really have to take a look at all the details, except for this one line that really makes the difference, because a square is a square, after all. So I initialize my base class with the square enumerator. Again, I have a couple of free functions, translate, rotate, and draw, that allow me to do all the important things with this square. Now, with all this mechanics in place, I'm now actually able to draw many shapes. And that's what my drawAllShapes function is doing. So drawAllShapes takes a vector of shapes, not just somehow, but by means of pointers. So a vector of shape pointers, unique pointers, of course, because else people would start throwing things. And I can draw them all. So how do I draw them? Of course, I first have to iterate over this vector. So there's the for loop, go over all the shapes. Well, and I have to ask nicely. Because at this point, I just have shape pointers. So I ask, what are you? And, well, if it's a circle, so if I get circle back, then I will draw a circle. Of course, I have to transform this shape pointer into a circle pointer by means of a static cast. Okay, you're a circle. I convert back, get a circle pointer, put this into the draw function, draw this circle. And if it's a square, I do the same. I just static cast to a square pointer. And this works. This works. This is what I can prove in the main function. I first abbreviate the vector of unique point of shape a little bit. I call it shapes. And I start by creating an empty vector of shapes. Then I add a couple of shapes, a circle, a square, and another circle. And then I draw them all. And it works. So now, of course, you would have to let your fantasy play a little bit. There is now beautifully drawn, beautifully colored shapes on the screen. It works. Amazing, isn't it? Okay, the reaction is a little bit different than what I expected. People are now staring very accusingly in my direction. Is this for real? So you're not really sure what to say. Seriously? Okay, some people actually look very, very terrified at this point in the sense of, oh my God, is this real? And some of you are actually even beyond that. Okay, there seems to be a problem that all of you kind of feel. If you don't see it directly, you feel it in your guts. And you have support. So Scott Myers, many, many years ago, in his small C++ book, essentially said about this kind of code, this kind of type-based programming has a long history in C. And one of the things we know about it is that it yields programs that are essentially unmaintainable. Unmaintainable. That's the key word in the sentence. Of course, he's talking about change. Because that's the one thing that you should always keep in mind when you write software. Things change. Software changes. And if you have to change software, you want to change it simply. It should be easy to change software. Because after all, that's the truth in our industry, software must be adaptable to frequent change. That's the word. It's in the word. Software. The soft basically indicates it should be easy to change. Now, of course, you immediately spotted why this is a big problem in our example. What if you add another kind of shape? Say a rectangle, or ellipsis, or whatever shape you like best. So, what do I have to do? First, I would have to touch the enumeration. And that has quite a lot of consequences. This little line actually triggers a lot of recompilations. For instance, the circle. It has to be recompiled. Simply because if this enum changes, anything could change. So this now could be a different value. It could have a different size. And everything could change. So yes, we need to recompile the circle. We, of course, also need to recompile all this functionality. So the translate, rotate, draw, all of this depends on circle. The square needs to be recompiled. And of course, for sure, also the draw all shape stuff. It also, however, has to be touched by adding another case statement. So the case, rectangle, and I would do the same, what I've done before for rectangle. Again, something where you cringe and feel like, this is not great, this is definitely not something that I want to do. Your argument is, this is duplication. A violation of the try principle, the don't repeat yourself principle, but it's actually something far worse. And that's exactly what Scott Myers talks about. This kind of switch, this kind of structure, this is not just in one place in the code. It's everywhere. In order to add a new type, you would have to go through the entire code base and you would have to change many, many files all over the place. Now, some of you grin and say, it's a switch. It's a switch, and so the compiler tells me what I have to change. It's not that bad. Okay. Probably not for you, because you are nice people, you would use a switch in this case. But what about your colleagues? Yeah, exactly. What about the people who do not come to CppCon because they do not care about good code? So they might actually have an if-else-if gate. I know the compiler does not give you any indication about something's missing, and you would be hunting for problems for weeks. So that's exactly the real problem. And so you're thinking, isn't there something better? Isn't there a better approach that we can do this? And of course there is. Yes, object-oriented programming. So this is so much simpler if we just make the shape a real base class. So this shape base class is now a base class with a pure virtual draw function. And the enumeration is completely gone. Completely erased from the program, and there's no traces left. The circle class publicly inherits from shape, and for that reason has to implement draw. And of course has to deal with the implementation details. That may be a disadvantage. The square also deals with draw now, because also here it's a shape. But, well, take a look at draw all shapes. It's so much better, right? So much more beautiful, so much more concrete. And it's totally oblivious to the fact that there's circles, squares, rectangles all over the place. This is, easily extendable by new kinds of shapes. The main function, by the way, is exactly the same. No changes down here. So it's definitely easier. Definitely easier. And, so that's the solution. Object-oriented programming. Now maybe for many problems, but unfortunately not for all problems. Object-oriented programming has one particularly nasty disadvantage. Adding types is kind of easy, but adding operations is kind of difficult. So if you want to add, in addition to the draw function, a serialize function, translate and rotate, so the functions that I pointed out before, then I would have to introduce them as virtual functions in the base class. Now, some of you say, okay, where's the problem? Well, then you are not really working in a code base where a lot of people actually depend on such a base class. This kind of dependency on a base class is kind of critical, because if you add a pure virtual function in a base class, everyone has to react right away, else the code doesn't compile anymore. So if you put this function in there, then actually other people have to start working. They have to deal with this problem. And they don't like this. They have a lot of work anyway, and now they're forced to implement these virtual functions. And so this is truly difficult. This is a problem that object-oriented programming does not solve particularly well. And indeed, so adding operations is truly difficult because it's intrusive. You have to add something to the base class. You have to change the abstraction. And there's something else. By doing this, by adding a lot of virtual functions in the base class, you're actually amassing, accumulating dependencies. So derived classes have to deal with all of these little problems that they actually not really want to solve on their own. Why should I deal with draw? That's a different problem. That's a totally different aspect. How should I know how to serialize? That's a different aspect. But I still couple them together in this one big interface. So, generally speaking, in dynamic polymorphism, you have to make a choice. And this is the two choices that you've seen before. If you want to add types, then you have to design for adding types. Or alternatively, you have to design for adding operations. But this is a choice, a serious choice that you have to make upfront. And it's kind of hard to go back. And so if you use a base class in this form, you are basically optimizing for the addition of types, but not for the addition of operations. So I have actually talked about the addition of types on Wednesday, and I had a talk called Type Erasure, the implementation details. In this talk, I told you how to implement this problem means of type erasure, because this is the right solution, the value semantic solution for adding types. However, now in this talk, I actually want to show the other side of the design space. So for the rest of this talk, let's assume that I actually want to add operations easily. Not just somehow, so like, okay, I have to change here and here and here. No, it should be so easy that everyone can do it. It should be totally non-intrusive. It should be possible for everyone. However, changing interfaces in object-oriented programming is difficult. That's exactly what we've seen just by means of this shape base class. And so apparently, object-oriented programming is the wrong choice. Or is it? Well, of course, design patterns to the rescue. And now I'll pick up this book, the design patterns book, the so-called Gang of Four book, released in 1994. And these four authors, what they've done is they have basically collected design patterns. They've not invented them, they collected them. They took a look around in many code bases, took a look at different solutions, and if some solution appeared often, recurringly, then apparently it was some kind of pattern. And then what they mainly did was to just formalize this, give this pattern a name, extract the structure, and describe it as, well, a formal thing. So I now take a look at this book and I pick out one of the design patterns, the visitor design pattern. And now this is exactly the UML diagram that the Gang of Four presents to us, which is not simple. Not really. There's a lot of concrete classes down here. There's a lot of classes where it's not quite clear what they are supposed to be. So a visitor, an element. So I simplify that. And I simplify this by adapting this to our problem. And so I start on the right-hand side and say we have a shape base class. So this shape base class may be the base class for many, many different kinds of shapes. Circles, squares, and please consider there is a few more, like rectangles, ellipses, triangles, you name it. These classes do not have any operations except for special things like get radius, get side length. They do not know about drawing, they do not know about rotating, translating, serialization, not at all, because this is the things that I want to add externally. However, as we've seen before, adding something to base class is difficult. It would actually put all the people that derive from the shape class, put them to work. And so now I extract that. I identify the addition of operations as something that changes, something that should be isolated and extracted. And that's what the visitor base class is about. And I call this shape visitor, because after all, it's a visitor on a shape. And this shape visitor represents an operation, a very general thing. Yeah? This is now an operation on a shape. On specific shapes, so the shape visitor has a visit function for every shape on the right-hand side. So right now there's two, so I have two pure virtual visit functions, but of course there could be more. So if I have a rectangle, ellipsis, and a triangle 2, then I would have in total 5 visit functions. Now this extraction, this isolation of change, that's actually what the single responsibility principle is about. So this is pretty much what design patterns usually do. Design patterns identify one aspect that changes, and isolate them. And now in our case, in our example, for this design pattern, it's just about operations in general. And this isolation now enables me to add many, many operations. I can now add a rotate. I can now add a draw, a serialize, whatever operation I desire, I can now add this externally. And not just me, anyone can do that, non-intrusively, because this basically fulfills this open-close principle. I have now designed for the addition of operations. This is now suddenly simple. And by the way, I say you see one draw, but of course there could be many draws. One by means of OpenGL, one by 3DX, this library, that library. There can be many, many operations. Great. However, right now we are missing one detail. We cannot really apply these operations on a shape just yet. We need one more thing. On the right-hand side, we add an accept function. And this function is, so this is the traditional name. Of course, you can name it as you want. But an accept function accepts a shape visitor. This accept function doesn't really have to do a lot. On the contrary, it's actually just calling the according visit function. So in the circle derived class, we would simply call visit on this. The this pointer is, of course, a circle thing. It would trigger the first visit function. The visit function, or this here, this call on the square side, this would, of course, trigger the square visit. And so this would dispatch to the right behavior. All right, now this is the visitor design pattern. It is focused on the addition of operations. Easy addition. Now, if you see it like this, it actually looks amazing. It really looks great because it appears to actually solve all the problems. I have two inheritance hierarchies. On the left-hand side, I can add operations, and on the right-hand side, I can add types. Hey, that's actually a one-for-all solution, isn't it? Of course, we usually wish that there is a solution for all the problems, but, as you should definitely keep in the back of your mind, every design has an advantage, or advantages, but also definitely always disadvantages. And so in this particular case, we actually have a couple of disadvantages. And first and foremost, the fact that on the right-hand side, I just have an inheritance hierarchy, which apparently allows me to add types easily, that unfortunately is an illusion. That doesn't work easily anymore. So imagine that I want to add a rectangle again. So I would, of course, here on the right-hand side, I would add a new class. I would derive this from shape. Good so far. But now, of course, I have to implement accept. How do you do that? Of course, I have to now change the left-hand side hierarchy. I have to add another visit function. This visit function, however, would again be in the base class. And we talked about this before. Changing the interface causes a lot of rework in all the deriving classes. Not a good day for everybody who implemented the shape visitor. So, implemented the derived class. Therefore, no, we cannot easily add types anymore. We can add operations, which is now kind of an open set, but we cannot add types anymore. This is now a closed set. So, this is definitely a disadvantage, and this kind of becomes obvious if we take a look at the dependency graph. So on the left-hand side, on the top left, there is the shape base class, and circle and square, of course, derive from that, and so they depend on the base class. So the arrow points towards shape. But the shape class itself depends on shape visitor, so it depends on this class, which, however, in turn depends on circle and square. So seriously, there is a cyclic dependency. So here, this is the cycle with a square, and down here, this is the cycle with circle. So this is also the reason why you sometimes hear about this visitor pattern as the cyclic visitor. There is a cyclic dependency. We're locking in the number of shapes, but for that reason, we actually can now implement operations quite easily. Now, everyone can do that. All right, let's take a look at how this is implemented in code. So I start with the shape visitor base class. I have two forward declarations. First, a forward declaration for circle and square, simply because, well, I need them. In the shape visitor, I need them. And however I arrange the things, I will always need some forward declaration because of the cyclic dependency. Apart from that, it looks exactly as you expect. It has a virtual destructor and pure virtual visit functions. The shape class is, well, it's the right-hand side base class, so again, it's a base, but this time it does not come with draw, serialize, and all of these dependencies, but it actually just has this very simple accept function, which is implemented in circles, by just, well, calling visit with this, and of course on square. So these classes suddenly become totally free of any dependencies, of any operations that they don't want to know about. But now we can implement operations kind of easily. So draw is deriving from the shape visitor and implements the two visit functions. So however this needs to happen. Draw all shapes still takes a vector of shape pointers and traverses all of these, but it doesn't do anything specific, a circle or square specific anymore. It just says accept this visitor. Please do this draw. And of course, there can be more arguments, so draw is probably not just, it's not empty. It might get a color, a texture, whatever you want to do. And this is now applied to this particular shape. And interestingly, still, the main function didn't change. It's still the same thing. So we'd now draw circles and squares without any changes here. Everything would be resolved by the visitor hierarchy. So there's definitely a couple of really, really great advantages. So first, we are now enabled to add operations non-intrusively, easily. And that's essentially the idea of OCP. And also, very, very effectively, we have isolated all the implementation details, drawing, serialization, and all these things that you do not want to deal with in every kind of shape. We've externalized this, which I said is the single responsibility principle. But I already mentioned that suddenly we cannot add types easily anymore. And actually, suddenly we're restricted to the public interface of the types. So draw can only use the things that a circle or a square provide publicly, which I never found to be a huge problem, but of course it depends. It depends on the application, and perhaps sometimes this is truly something that restricts. But there's one more thing, which definitely isn't great. You now have to call two virtual functions for every single operation. So the first virtual function, of course, is accept. So apply this visitor. In turn, this would call the visit function. So by passing some this pointer, we'd go to the right visit function up here, and that's of course the second virtual function call. So even for some very, very simple operations, like just change the center point a little bit, we would have two virtual function calls. So from that perspective, it's we can already anticipate that the performance is not particularly great. Okay, there's a couple of other disadvantages, but they're more implementation specific, not design specific. This kind of programming always requires a base class. And that in itself, unfortunately, is intrusive. So all the shapes, circles, squares, have always to implement the shape base class. If you have a third-party shape, you would have to write an extra adapter to make this happen. Intrusive is never really great. This kind of style also promotes heap allocation. So strictly speaking, we do not have to put something on a heap, so we do not have to allocate dynamically, but we usually do. And if we do, then of course we are required to manage the memory. That's the reason why I used unique pointers in the first place. So there's a couple of problems. And you're not excited right now. Okay, the design pattern as such is great. It allows you to add operations, and if this is what you're looking for, thumbs up, great. But the style, this 1994 style. Sure, we've thrown a couple of smart pointers at the solution, but this doesn't really make it modern. This doesn't really make it what we desire. We want to have something that is simpler, cleaner, something that actually feels like modern C++. What if I told you that there is a modern solution? An amazing solution, a really nice solution? We could use a variant. The variant, we can actually put circles or squares in there. So a variant of circle and square now contains either a circle or a square, and therefore acts as some kind of abstraction. And of course, there could be more. This could be a variant of many different shapes. I stick to my two that I have. So it's an abstraction of shapes. What's a great name for an abstraction for something like that? A shape. And you do realize, hey, this was the name of a base class. Absolutely. We now have a different kind of abstraction, a different form of abstraction, and we're going to refactor accordingly. So let's take a look how this actually now works in this modern C++ form. So again, I start with a circle. And you note there is no base class before that. So that's the first class we look at. So no enumeration, no base class, just a circle. And indeed, there is no base class. The circle is just a standalone class that has a radius, that has a couple of other data members perhaps, but also that has nothing and does not know anything about drawing, serialization whatsoever. It's just a circle, just a geometric primitive that doesn't have to know about anything else. Now, of course, the square is super similar, and all the other shapes will be too. The square has just a side length instead of a radius, else it's pretty similar. Imagine that you have a third-party thing. It might actually already work. You would not have to change code. You would not have to add code. Cool. Now, we can now add operations. Just as with the square classes, this does not require any base class. It's just a class that I write at any point where I need this operation. Freely, non-intrusively. So again, we have this property of being able to add operations easily. All we have to do is we have to implement a function call operator for circles and squares, which indeed looks super similar to what we have seen before. Major difference, before it was called visit, now it's called function call operator, which is a very, very reasonable choice because this allows us to use a lambda too. If you have a lambda right away, well, use the lambda. You do not have to write a class. It might be convenient, but you can use anything that is callable. All right, then we have this line here, the variant of circles and squares. Now this is a value. I do not have a pointer to a circle or a square. I also don't have any pointer to base. I have a value, a variant that either contains a circle or a square. And so it's not surprising that I now indeed work with these values. Draw all shapes now takes a vector of shapes, very naturally, which is, from a language point of view, amazing. Many shapes is just a vector of shapes and not something in between like these pointers. So I have a vector of shape values, I traverse all of these values and I apply a visitor. By calling a function that already promises what it does, we visit this variant. And we visit it by passing a visitor, in our case, draw. So let's draw this shape in whatever color. Now for the first time, we actually change something in main. Okay, let's just set that. We now actually change something in main. But we do not make this harder to read or less comprehensible. Now actually we clean this up quite a bit. I now put values inside this vector. So I have a vector that takes shape, so I can put a circle inside, a square, another circle. And that's usually the point where people are just smiling. This is beautiful. This is beautiful. This is what I want my code to look like. It's natural, it's intuitive. Oh, amazing. And immediately you love your language again, right? No pointers, no base classes, but values. So no pointers, no allocations. This is what I missed, but truly values. And your code suddenly is so much simpler. But now, is it truly a visitor? Well, actually, it's even a little better. If you take a look at the dependency diagram, then it looks very, very similar indeed. So on top, we have circles and squares, which do not have any dependencies. They're standalone. But the variant needs them. The variant needs the circles and the squares and all the other shapes. This is now what I built my operations on. So still, the operations, the implementation details are on the lowest level of my architecture, of my design. Anybody can add them freely, non-intrusively, and there's no dependencies anywhere. So from a dependency point of view, it's indeed like a visitor, like the classic one. With one change, which however is absolutely amazing, there's no cycle. There is no cyclic dependency. So anyone, anywhere can just add another abstraction. So say that we have an ellipsis 2, and we need an abstraction that represents a round shape. I can just add that freely. I do not have to change any base class. I do not have to go back and say tell circle, I have derived from this thing too. No, I do not. I can just freely add a different kind of abstraction and be good with that. So this is definitely an amazing advantage of this non-intrusive design. So to summarize, there's many advantages. There is no inheritance hierarchy left. It's totally non-intrusive. There's also no cyclic dependency anymore, which is great. This gives you a lot of implementation flexibility, and anybody can do something. The code therefore becomes so much simpler. I believe this is a great example for the KISS principle. And there's no virtual functions. There is no pointers or any other indirections. There's no manual dynamic memory allocations. A note that I say manual, so you don't allocate with, for instance, a make unique. Somewhere inside a vector, of course, there is a dynamic memory allocation. And there is no need to manage any lifetime. It's done automatically. After all, we have values. And so, of course, there's also no lifetime-related issues anywhere. No need for smart pointers, and the performance actually might even be a little better. An amazing list. This is what we want. This is what we actually desire in our code. Yeah, but now I've mentioned performance. I know. When I say the performance is better, of course, people see this as a red flag. Yeah, show us the performance. Okay, I will do that. But you might have been to one of the other two talks that I've given, and you might know what I think about performance. It's always a tough topic. You show some performance results, somebody complains. So, also for you, I will show you performance results if you do promise me that you do not take the following results too seriously, and just as well an example for performance, well, basically on my machine. So, do you promise that you will not take this too seriously? All right, then I take you by your word, right? Else we're not friends anymore. So, performance, I should quickly give you an idea what I actually benchmark. So now I have 4 different kinds of shapes: circles, squares, ellipses, and rectangles, which I believe is a little more realistic. I have 10,000 of these, but randomly generated. So it's not necessarily 2,500 of each, but well, probably close. I do 2,500 translate operations, which I specifically chose because it's a very cheap and a very simple operation. It's so cheap that we actually see a difference in these different solutions. If I would use something that is very expensive, perhaps a draw, then the performance would be pretty much equal. So this is a pretty important decision. And I use these 2 compilers, and I additionally use this machine. So something that may be interesting for you. And I said, you will have a different machine, so you'll definitely get different results. But here we go. And I benchmark everything that we've seen so far. And so I start with this enums solution. Yeah, I know, it still hurts to think about it, but the performance is not bad. So this is the performance that I get on my machine. And please do not make this a race between GCC or Clang, it's just a comparison. If we switch to an object-oriented solution, which I have to say in this context is a little an outsider because this is not about adding operations, but still the performance is interesting, then yeah, performance drops a little bit. Especially on GCC, it's obviously more expensive. And that is because of the introduction of virtual functions. There is just a little more overhead. There's less potential to optimize. It's harder. However, if we turn towards a visitor, 2 virtual functions, then the performance drops significantly. And especially something that you will feel in Clang, it definitely is so much slower. It feels so much slower. And unsurprisingly though, there's no potential for optimization anymore. 2 virtual functions really take all the wind out of the sails of a compiler. And so you will be very, very happy to hear that a variant is actually much faster. And this is std variant. I actually tried another variation. I tried an mpark variant. So mpark this is a shortcut for Michael Park, who has a freely usable variant on GitHub. So mpark variant, which actually turns out to be even faster. Amazing. And if you see this, I believe this is where you now cannot stop smiling for the rest of the day. This is great. It's more beautiful and faster. What else do you want? But now I know I have piqued your interest. Why is that so fast? How can that thing be so amazingly fast in comparison to the other solutions, including the enums solution? Well, let's just take a look. Let's take a look at this mpark variant. So this is the GitHub page. And we now basically take a look at the source code, look around a little bit. And yeah, there's 2,000 lines of code. Fast forward, we take a look at the visit function, which does a switch. A switch. And I know at this point you don't know what to say. But this is what we do not like. You do like that. Because it's hidden somewhere in some implementation that you don't control. So I say it may be based on a switch. This is what Michael Park does. I do not say this is what all the implementations of visit do. And there's a lot of discussion around this. So let's skip that. But we actually use good old procedural programming. And we don't care. We do not care that this is a switch, but we actually feel this is absolutely correct. It's fast. And this is code that is generated. And so you don't have to maintain that. You don't have to go back and add another case and manipulating all of the code base. It's generated code. And therefore, this works so much better. And of course, this can be significantly faster, especially if the surroundings are also done quite reasonably. Amazing, isn't it? So yes, actually, surprisingly, we're back. We started at a solution that you felt was awful. We turned towards object-oriented programming. And object-oriented programming actually turned out to be better. But it didn't really make us happy. Too much overhead on in many directions. And now we're back. Back to procedural programming, but now we like it. I actually feel it's the right solution. So now you're super happy. So this is the solution that you've always been looking for. This is how a visitor should look like. And so just a short comparison. The classic visitor is intrusive. It's a base class. You cannot simply add something new. You have to change existing code if you want to do that. Whereas the modern version is non-intrusive. You can add things on the fly if you want to, both the abstractions, but also the operations. Then, the classic visitor definitely is an example for reference semantics. It definitely is. There's a lot of pointers, a lot of reference floating around because we always work with a pointer or reference to base. That's how it works. The modern version, however, that is quite firmly value semantics. So we're basing everything on values. And suddenly things get so much easier and faster. Then the classic visitor is an OO style, an object-oriented programming product, whereas the right thing, I would say, is a procedural style. Some say perhaps it's a little going the functional direction, but it definitely is the good old thing. And from performance perspective, I think this was obvious. The classic visitor was kind of slow because of the many virtual functions, also the scattered memory access because everything was allocated manually and all over the place in memory. Whereas in the modern version, there's not a single virtual function, not a single pointer. And also you didn't see any allocation. This is why all of the data, and really all of the data is just in this vector, which is from a memory perspective, the absolute optimum. So it is fast. All right. I should, however, I know, of course, I know that you know right now, you look very calm, but deep within you are celebrating value semantics in modern C++. But I would be a bad trainer if I do not talk about the disadvantages too. Every solution has an advantage, but every solution has a disadvantage too. And so it's not a big surprise that this also happens to variant. So the first thing is hopefully kind of obvious. It's a visitor. And as a visitor, you cannot add types easily. Correct. The visitor has in angle brackets the list of all the types. It's a closed set. And if you change that, of course, just as before, you have to change everything all over the place. Yeah, all the operations and potentially much more because a variant is pretty revealing. The variant also is not a particularly great solution if you have types with a vastly different size. So circle and square in my examples had the same size. Rectangle is pretty similar too. But if you imagine any kind of shape that is huge, then actually you might waste a lot of space by putting this in the variant together with circles and squares. This is where you have to pay a little attention. However, this is something that you can solve. And there's definitely three possibilities. And the first one is that indeed you revert to pointers. I know this messes up the beauty a little bit. Back to pointers that you have to manage again. But of course, the size is small. A pointer has a size of 8. But still, I would not say that this is what you should do. Yeah, we will use pointers, but we'll kind of hide them. And there's two design patterns that help here. The first thing is the proxy design pattern. So write a little class that represents this big thing. Represents in the sense of it pretends it's that thing, but it hides this big thing behind a pointer, but somewhere inside. So you still have values, a value, but you don't really realize that actually it refers to something bigger. This is what you do if you cannot change some type. You wrap something around that. But alternatively, if you actually can change a type inside, then you can revert to the bridge design pattern, what you might know as the pimple idiom. That is definitely a great use of a pimple. It would reduce the size, hide implementation details, and all the data members behind the pointer, and therefore reduce the size to something that fits pretty well into a variant. Also together with all the other alternatives. Okay, and then dependencies. After all, it's about breaking dependencies, but now truth be told, a variant can actually reveal a lot of information. And sometimes this is unfortunately pretty hurtful. In my example, in order to have this variant, you need the full definition of a circle and a square. So not just the declaration, not just the forward declaration, for instance. No, you need a full definition. And of course, if you now use this variant in a lot of places, all of these places know about these dependencies. And if you change something, then again, a lot of code might have to recompile. So this is definitely something to keep in mind. It might not be a problem, but it could be. And of course, depends on how you use that throughout your code base. Again, there's a simple solution: revert to pointers or any of the other things, hide some implementation details behind this opaque pointer. But of course, the effect is that there will be a performance disadvantage without question. This is an obvious thing. All right, cool. So we have now seen the good old visitor and we have seen the modern visitor. But I've now made a statement before. I've made the statement that in dynamic polymorphism, you have to choose between adding types or operations. Note the or. It's a choice. You cannot have both. And also note dynamic polymorphism. In static polymorphism, there's no problem. Dynamic polymorphism. Is this really true? Is this really something that I always have to choose? Isn't there something that perhaps can do both? Well, okay, truth be told, there is. And I'll show this to you. I do not believe, though, that you will be super happy. No, I don't think that, but still, let's take a look in order to get an impression on possibilities. And so I now introduce you to a different kind of visitor, the so-called acyclic visitor. Now, this is a little more complicated, but still I use shapes, of course. What has primarily changed here on the left-hand side is that I have split the visitor base class into many. In the center is now something that is called abstract visitor. And that abstract visitor is actually totally void of any operation. So it's the dump base class. It cannot do anything. Still, we will need that. This is important, but this is truly totally abstract. And then there is a visitor base class for all the kinds of shapes. There's a circle visitor, there's a square visitor. The circle visitor introduces the visit function for circles. The square visitor introduces the visit function for squares. And of course, please, consider that there's many more shapes. So there's one base class for any shape. There could be rectangle visitor, ellipsis visitor, etc., etc. Now, the operations like rotate and draw, they definitely, first of all, always inherit from abstract visitor. And that is the one base class that all the operations need to inherit from. So this is the central base class. But now these operations inherit from all the visitors that actually want to support. So rotate, for instance. Let's start with draw. Draw, for instance, actually inherits from both square and circle visitor, because we want to draw both circles and squares. But rotate chooses not to inherit from a circle visitor because, well, rotating a circle is boring. So we just support squares. And so we can now selectively choose what we want to support, which of course is giving you flexibility. Imagine that on the right-hand side now I change something, that I add a different kind of shape, say a rectangle. For that purpose, I would add a rectangle visitor. But this doesn't require you to do anything at this point. You can slowly but steadily make all these operations inherit from rectangle visitor, but you're not forced to do this right away. So you have a little flexibility. There's not such a strong dependency. You have torn this apart a little bit. So things get easier. It is easier to add new kinds of shapes, whereas don't say it's easy. It's easier. Again, there's something missing on the right-hand side. On the right-hand side, we now introduce, one thing first, of course, this is what you thought about before. Of course, we would not have many visitor classes. We, of course, today implement this as a template. One visitor base class for all the different kinds of shapes. This is how we do it. So now, on the right-hand side, the shape gets, again, an accept function. This shape, however, expects an abstract visitor. The abstract thing. Which means that the shape does not know about circles and squares any longer. So it's totally independent. However, now, and this is where people usually start to feel uneasy, we now have to implement this accept a little differently. So, for instance, the circle in the accept would first try to convert this visitor into a circle visitor. And of course, this does not fit the picture perfectly anymore, but you get my point. So the circle visitor, it could be a base class, but it could not. So we try. Can I convert that? If I get a valid pointer back, then I am supported. This thing knows what a circle is, and I can simply call visit. But if the dynamic cast returns a null pointer, okay, this thing doesn't know what a circle is, I just cannot visit. A dynamic cast. A dynamic cast. Yeah, but in this context, this is actually required. Now, is this a sign of bad design? Because dynamic cast is always bad, isn't it? No, actually, this is okay. From a design perspective, this is perfectly okay because the circle simply asks, does this thing know me? So I do not couple things together that shouldn't know about each other, but the circle really sticks to itself. Does this know me or not? So it's a technical detail, but it's not something that causes these usual unfortunate dependencies that many people unfortunately introduce with dynamic cast. And so the dependency graph looks this way. Shape, the shape base class, the abstract visitor, and also this templated visitor, they're all on one level. There is truly no dependency, and everything else is somewhere below. And doesn't couple. Circle, square, and any operation are totally independent. And so the circle just asks, does this thing know me? And so it does not couple to anything else. This is why it's okay. Okay from a design perspective, but not okay from a performance point of view. Every design has an advantage, but a disadvantage. And in this context, I believe I can very quickly show you that this is not what you're looking for. You see that the scale has changed. This acyclic visitor is slightly slower. Slightly slower. Okay, let's be honest, it's terribly slow. So the first time I actually ran this benchmark, I thought I had built in an infinite loop. Of course, yeah, so I stopped it, I checked my code, I ran it again, still an infinite loop. I think at the fourth or fifth time only, I actually waited. And then eventually it finished and I realized, whoa, this is slow. So a dynamic cast is slow, especially in this context, because what we're doing here is not just a simple downcast, not just a cast from base to derived, but we do something that we call a crosscast. We cast from one base class to another base class. And of course, this is quite a journey. We have to go down, perhaps even more down, and then up again, slow. Now, it could be faster, and apparently there is faster implementations, but in comparison to all the others, it's just terribly slow. So perhaps this solves the dependency a little bit, but you would have to seriously consider to use that in production code. If you really do not care about performance, perhaps sometimes this gives you an advantage, but generally speaking, I would say, nah, probably the others are better. Okay, and so allow me to summarize. Yes, if you want to add operations, if this is what you desire, if this is your design goal, then the visitor decide pattern is the right choice. But of course, if you want to add types, then please do not use a visitor, which also should give you a little bit of an idea that a variant is not the tool that should appear everywhere. It should be design choice. Do I have a closed set of types? Yes or no? And you've also seen that, the right choice from an implementation perspective in this context is procedural programming. Object-oriented programming does some good. It works, but it's just the wrong paradigm in this context. So interestingly, the classic visitor design pattern is truly, as I said in the very beginning, an outsider. It's a special thing in the Gang of Four book. It's a workaround to the disadvantages of object-oriented programming in general. And so, today, please prefer the value semantics-based implementation based on standard variant. And last but not least, beware the performance of acyclic visitors. As a side note, I do not believe that after this you will use this a lot, but it definitely helps to know a little bit about the fact that it does exist. All right, with this I'm done, almost. Then, of course, I used the opportunity for shameless plug. You realize I love to talk about design patterns. I actually love to talk about design patterns so much that I actually wrote a book about that, which should appear in a few days. So unfortunately, it was not finished yet here at CppCon, but well, in a few days, end of September, there is the opportunity to read about software design. And you get an idea what this book is about. It's not about implementation details, it's about dependency management. And there is indeed a lot to say about that. So I go through many of the design patterns that you know, and we take a look at them, how are they implemented in modern C++, and also how do they actually change the dependencies in your software. Okay, so with this I'm done. Thank you very much for the attention. All right, and I'm happy to take questions if there are any.
Then we have an online question. With modern solutions, it seems we can use visitor design pattern for adding types. Why is it a disadvantage?
I do not understand the question. Why is it a disadvantage to use the modern way?
It seems we can use the visitor design pattern for adding types. Why is it a disadvantage? Is how the question is written.
Okay, then I take a guess. You can add types, but it's always more difficult. I do not say that you cannot in the sense of it's impossible, but of course it affects a lot of places in your code. So if you truly want to be non-intrusive with regard to adding types, you probably should consider something like type erasure, which I talked about on Wednesday. There is another talk that deals with that problem. So essentially it's about changing in a simple way, easy change. Please.
Yes. In the latest example, the acyclic one, right, the one that's very slow, you said that we can add easily shapes, but some operations will just not be supported. I guess there's some default operation that will happen in those cases. Why can't we do exactly the same thing in the variant case using, well, the requires clause, right? We can do, if you can do draw on this type, then draw, otherwise, I don't know, log or something. And get the exact same advantages as this one.
You definitely can do something like that. You can decouple a little bit because you have the freedom to do so. In a classic visitor, you have to deal exactly with a given set of visit functions. But because you now have flexibility in implementing your visitors, you can definitely provide default cases much more easily. If you do have default behavior, which is exactly the little problem. This particular context here, but when I said not, it's easy. I said it's easier.
Easier, yes.
If you do have some default behavior, then you can do something. Still, it might not be what is expected. If you now add serialize, and serialize cannot serialize a circle yet, it's kind of awkward too. And that's the same thing with the variant. So default behavior sometimes works if there is default, but in a general context, it's perhaps surprising. And I would argue that it might be a risk of substitution violation.
Okay, thank you.
Which we can talk about later.
Yeah.
Please.
In the 00 version, the member functions have access to the private internals of the class.
Yes.
How do we enable the visitors to also get that access?
This is the tough part. So this is one of the weak spots. This is why I listed this as a disadvantage. If you do need access to the private section, then I do not have a great solution. Either you enable access somehow by additional getter functions.
Yeah.
Sometimes it's painful because you want this to be hidden, you want it to be private for a reason, or you have to do some hacky things. What I mean with hacky things, it's in a good, hacky already sounds bad, is that you indeed give your visitors access to some private things. But of course, this would increase coupling again. Now suddenly your types would know about the visitors. This was the point in the first place. I can add them freely without it being intrusive.
Via friends declarations or?
That's what I mean.
Yeah.
I just pointed out this is of course a technical possibility, but from a design perspective, not desirable. And so I don't have a good answer. I don't have a good solution.
Okay, thank you.
Thank you. Awesome talk. I have a question on the performance. So the enum solution also uses switch case, and the MPark variant also usage switch case. So where is the gain coming from?
So yeah, the gain comes from the memory layout, because in the enum solution I still had pointers. The memory was still scattered anywhere. Whereas at the very end is actually gaining because everything's nicely stored in a big vector.
Got
I
it.
did not analyze this in the detail, in big detail. This is indeed my major point to say value semantics is not necessarily bad. Performance can actually improve because of that.
Thank you.
Thank you for your talk. For a cyclic visitor, I'm kind of thinking this another way to set up inheritance. If you will set up inheritance for visitor with virtual inheritance for abstract visitor, you might speed up dynamic cast, or might not. So if instead of dual inheritance for every concrete visitor, you can use a single base for them, all of them.
I get a point. I did not try virtual inheritance. And in fact, indeed, in my production, in my career, I have seen this in use very, very, very rarely. It's not really what people think about first. So I probably didn't. So I don't try. I didn't try, I don't have an answer.
Yeah, also for enum solution, virtual inheritance would help. Because then if you have some class circle and big circle which inherits from circles, then visual inheritance will allow you to set proper enum into the base class.
But of course, perhaps on another scale, it also affects performance negatively. So indeed, this is something that you would have to try.
Yeah, you need to try. It's like experimental thing.
Exactly. It's an interesting experiment. I might try that. Thank you.
So.
All right. That's it. Thank you very much.